No one's here yet, but I think I'll be here early just in case anybody wants to get in. I'm going to go ahead and record this in case someone asks questions and someone wants to see the answers to that later. So it might be some dead time for the first several seconds of this. Not several minutes. Class is not supposed to start for another 8 minutes. I will actually pause it until you come on. Oh, there they are. Never mind. Come on in. Hey, Gage, Devon, y'all have any questions?
No, not right now.
That's cool. Sounds good. We're way early. I just opened up in case anybody had any questions since I've been away from so long and didn't necessarily have an office hour this morning. No one asked me for it, but normally I have an office hour from 8 to 9. So got some more people coming in. This is just 3 so far. Well, y'all are all free to ask me any questions. Like I said, this is your time to ask me anything if you have anything. Class doesn't start till 9, of course. I'm working on our grade book, trying to make that nice and neat. All right, my alarm says it's officially 5 minutes till when we're supposed to start, so we're getting there. I'm not ignoring you guys. Well, I sort of am, but like I said, if you have any questions, make sure you ask me. This is your free time to ask me whatever you like. Lab or lecture, mind you. I hate this. It gives me 2 copies of every time. It just about aggravates the heck out of me. Maya's here. Maya's here. Jelani's here. As you just coming in, I told everybody feel free to ask me any questions while we wait for everybody else to get in. We've got about 4 more minutes for class starts. But this is your free time to ask me any questions, sort of like an office hour. Also, once I get you started on your lab, telling you how to get this started, which y'all are somewhat familiar with already, I'll have all that time there in case you want to ask me class related questions, syllabus related questions, any of that kind of stuff. So meanwhile, I'm cleaning up our grade book for physics just to make sure I've got the right categories and the right scaling for them and all that stuff. So that's why I look like I'm busy not looking at y'all. Hope everybody has had a nice extra day off, and it's nice not coming to school today. I know that. It'd be cooler if I hadn't contracted COVID, but here we are. All right, got another student. Come down here, darn you. It's Jordan. Still got about 2 more minutes. Those of you just coming in, I told everybody this is an open question and answer session for you guys while we wait for the beginning of class. Also said after I introduce you to the lab, we'll have once you get started helping your lab group or whatever, we'll have more time for you to ask me questions about lecture, the syllabus, and that kind of stuff. Any of the topics that we've covered are going to cover, that sort of thing.
I know for lecture, I have a class that ends at 1:50, so I just may be a couple minutes late to joining the Zoom meeting.
Okay, that's not a problem. Who's this speaking?
Jordan.
Okay. Oh, well, sorry, I didn't
It's
probably
okay.
noticed. I didn't even recognize you last week. You changed your hair color. It looks nice, by the way, but I just I was like, man, I know that girl from somewhere. I can't remember if I had her or not, but you look so entirely different. It's nice. It's a cool look, but like I
Yeah,
said, I
I took
apologize.
yeah, I took physics 1 in summer and then didn't take it in fall and then did it in
Yeah, I
spring.
remember even talking to you like in the parking lot last semester about not taking it, but like I said, it was weird because I was like, she said she was going to take it, but I hadn't looked at the roll. So literally last night I went there, oh crap, my roll. Hey, she's in my class this semester. So yeah, I'm a little special. I don't I don't work very well with names and faces very well. So anyways, yeah, that's not a problem at all. Obviously it's going to be a little bit dicey here trying to do lecture and all that good stuff, but the good news is lab, which is supposed to start in 1 minute, it's probably going to take me about 20 minutes to explain everything to you, and then I'll make little breakout groups and you guys can go off in that. I will stay here outside in case anybody has questions, but you can come out. Excuse me, you can come out and ask questions about anything you want regarding lab or lecture or whatever. It is being recorded, so if you have personal questions, maybe make our own little breakout room to do that in. That way it won't be recorded. But other than that, you've got me until about 10 till 12. And then at 12 o'clock, I teach the 241 class online. And then at 2 o'clock, I teach you guys again for lecture. So that's how that will play out today. Anybody have any other questions? So I'm finally setting up your groups, your assignment groups. We have homework group, we have the conceptual group, and we have the face-to-face tests group. And those are sort of what the syllabus tells us how our course is graded. Each of those have a certain percent, but I have to break them all up into that. But it's always a little bit of a pain in the butt to do at the beginning of the semester. So I'm currently finally doing that. And your grades should be fairly accurate throughout the whole semester, except when I throw in extra credits, because extra credits give you a boost or they leave you right where you are if you don't do them. But that sometimes doesn't show up till the end of the semester, just out of a nice little ace in the hole that I keep for my students, sort of like a father figure in case they get too cocky about how well they're doing, and then they throw off the final exam as if it's not going to be a big deal, and then they end up taking a C when they were ready for an A. So I shouldn't do that. I should just be a college instructor and let you have it. But I don't know, I feel somewhat paternal in trying to aid people, or at least parental if not paternal. So all right, it's now officially time for class to start. Actually just about 2 minutes past, but so does anybody have any questions before we get cracking on the actual spreadsheet review, which is the lab today? Hopefully everybody saw it in Canvas. Okay, those of you who had me or anybody else at TCC for PHY 241, chances are you did already do the spreadsheet review lab, or just introduction to spreadsheets, what it was last semester. This is called the spreadsheet review. So this should be somewhat familiar with you, but the main thing is your phone can do this. Oh, excuse me, not your phone. Well, actually, you could get your phone to do it, but your computer can do this. Your calculator that you have that's using class, at least if it's a big screen, I know it can do it. And I've actually seen evidence that some of the small screen computers, some of the TIs and the Casios, even with a small screen, can do statistics packages and analysis and stuff like that. But I know virtually every large screen computer calculator that I pick up has the nice little statistics package and a regression analysis package and that sort of thing. And that's what we're using here. We're going to be using something called regression analysis. So when you are first discovering some kind of scientific relationship, and it don't even have to be a scientific relationship, any kind of relationship, like maybe you've noticed that you have to drive, once a week to go pick up somebody in another state. And you notice that when you drive with an average speed of 65 miles per hour, you use more gas than when you drive with an average speed of 58 miles per hour, say. So what you've seen there is just by probably, if you were really a good observer instead of just someone who happened to notice all the hits and miss all the misses, but if you're a good observer, maybe you took notes and kept track of your miles per gallon each trip and your average speed each trip. If you did that and you did see some kind of relationship, you'd probably conclude that the faster I go, the lower the fuel economy. In other words, the more miles per gallon, or excuse me, less miles per gallon that you get. So high speed means less miles per gallon. That is the intro to a quantitative relationship between two variables. One of those you more or less call the independent variable, and the other one you call the dependent variable. And the dependent variable is always supposed to be on the vertical axis, and the independent variable is always supposed to be on the horizontal axis. So in this case, you're talking about miles per hour that you average from here to whatever place you're going to, and the other variable is miles per gallon. So in this case, I'd say you're making the argument that miles per gallon depends on the miles per hour. So I would put miles per gallon on the vertical axis and miles per hour on the horizontal axis, because that one's free to be whatever you want it to be. Now, when you make that plot, you've already got a sense that when one goes up, the other one goes down, meaning high miles per hour, meaning you're on the far right-hand side here. High miles per hour means a low miles per gallon. So you expect the line to do like this, or like this, or like this, or something like that, just so that as you get a larger miles per gallon, as you get a larger miles per hour, the miles per gallon decreases. Now that's just an inverse relationship. That's that's the lowest order of quantitative analysis you've got. Now the next step to make it a scientific discovery that's more precise, or one that basically creates a hypothesis that's falsifiable. So you actually need every hypothesis to be falsifiable. It doesn't have to be provable to be a scientific hypothesis. It just has to be disprovable. So if you are actually making numerical estimates of what it should be, and you can put in a certain amount of uncertainty and get out a certain amount of uncertainty, then your ability to falsify it just is a matter of, does it fall within what we expect minus the uncertainty and what we expect plus the uncertainty? If it falls in that little interval, then you could call that a success. And if it doesn't, you'd say that that hypothesis has been falsified. In order to get some kind of good, meaningful value of expectation, uncertainty, and uncertainty, remember it'll be expectation value plus or minus uncertainty. In order to get that, we need a formulaic response in some sense. So we found over time that a lot of these variables are very simply related to other variables. In other words, they could be really complicated crap, But in fact, they often turn out to be simple polynomials or trig functions or logarithmic functions, stuff like that. So we might say, let's call the miles per gallon E, that's going to be on the y-axis. And let's call the average velocity, miles per hour, that's going to be S, okay, for like speed. So E on the vertical axis and S on the horizontal axis. I know that's backwards for you. Let's do it like this, maybe. Okay. E on the vertical axis and S on the horizontal axis. You could say that E is equal to some constant times 1 over, or excuse me, equal to some constant divided by S. That would be an inverse relationship. E is equal to some constant divided by S. But it also could be E could equal some constant divided by S squared, or S cubed, or maybe even S, the square root of S. That would be acceptable as well. In fact, those are the simple ones. It could be the cube root, it could be the square root, and those are the simple ones because they're nice, either rational exponents or even, you know, whole number exponents. That would be nice. And there's no reason nature has to provide them in that kind of nice polynomial, but it turns out basically it turns out in large part, virtually every relationship we look for like that, at least in the physical realm, turns out to be a simple scenario of x to the -1 power, or y to the, or x to the -2 power, -3 power, -4 power, or x to the 1 power, x to the 2 power, x to the 3 power, or even 1/2 or 1/3 or stuff like that. Other than that, occasionally you'll find, you know, a relationship between y and x, or in our case, E and S, that might be a trig function, or that might be a logarithmic function or something like that. So those actually exist as well. But it's amazing that we happen to have all these neat functions we've made up, including the simple polynomials, that happen to work out to relate variables of real physical quantities that we had no idea even existed back when we came up, or when I say we, when human civilization came up with polynomials and stuff of that sort. So the next step after determining whether two variables are thumbs up, or thumbs up, thumbs down, thumbs up would be like, let's say the faster you go, the more gallons per mile. So in other words, the inverse of efficiency, miles per gallon is how much fuel consumption is related to fuel consumption. That's the E variable we were talking about. But you could also do miles per gallon, and that would be the opposite of that. But miles per gallon would go up as miles per hour went up. That would be a thumbs up relationship. And again, that's the rudiments of a quantitative analysis of one variable's dependence on the other. And then when you put some meat on it, like put a constant in front of it, raise it to a power, or put a constant in front, raise it to a power, put a different constant, raise it to a second power, so on and so forth. Once you do all that, it gets a little more robust, and it gives you the ability, again, to predict precisely what answer you expect, plus or minus precisely a certain amount of uncertainty, which we've learned about through propagation of error. And before that, we were using, you know, sig figs and stuff like that. But so that's the sort of holy grail, if you will, of experimental science, is when you first start studying things, you need to see how things depend on one another. So for instance, Enrico Fermi, once he actually started working in the nuclear physics area, it was basically a brand new field. So literally he went and did simple things like, hey, we can shoot these particles at these nuclei that we now know are nuclei of atoms. And from that, we can get an estimate of how big the nucleus appears to be. So he found, you know, basically the diameter of certain nuclei. And he's like, I wonder how that depends on, let's say, the atomic number, or how that depends on the number of protons, or how that depends on the number of electrons and all this stuff, right? So he just set forth doing experiments and then setting up graphs of size of nucleus as if that's the dependent variable, and then would plot that versus the number of nucleons. And then he'd try plotting that versus the number of protons. Then he'd try plotting that versus the number of neutrons and all that. And he would first see, is it thumbs up, or is it thumbs up, thumbs down?
and then he would look for what power it would be. This was also done, for instance, with Johannes Kepler when he was given the task of trying to figure out the universe. He already had an idea of the universe. Now, again, in this era of Kepler, the universe was essentially our solar system plus about, I don't know, somewhere between 7 and 10,000 stars we can see with the naked eye, all of which happen to be within what we now know of as the Milky Way, a small portion of the Milky Way. So they didn't realize there were other islands of stars. We didn't understand that until Hubble came along. Hubble the telescope, no, Hubble the person, not the telescope. Okay, but anyways, once he came along, we figured that out. But still, Kepler had really specific ideas about how the sun, the earth, the moon, the planets, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, that's all they knew at the time. We had very specific ideas about how that was laid out, and we had been using the Copernican, the pre-Copernican ideas, which were what they called the Ptolemaic ideas, which also came from Eratosthenes and Aristotle and stuff like that. But basically, all those have reached a conclusion that the Earth was at the center and all the other planets are orbiting around them. But when Kepler finally got some really good data, i.e., a guy by the name of Tigo Brown's data, he was confronted with the ability to do the computations himself, and he was trying to figure out some relationship between how big an orbit was and how long it took to go around the orbit, the period. So what he did was he plotted, let's say, period on the vertical axis and semi-major axis, which is sort of like the radius of an orbit, on the horizontal axis. And he'd plot them like that, and it didn't make a straight line. So he's like, well, that stinks. So then he said, all right, let's do the square of the period on the vertical axis and the semi-major axis on the right, on the horizontal axis. And he didn't get a straight line. And then he tried the cube of the semi-major axis and didn't get a straight line. And then he tried the fourth power and didn't get a straight line. And he could go on forever. But if you have some experience with numbers, you wouldn't have to go much farther. You probably wouldn't even need to have gone to the fourth power. Then he starts trying, let's leave t alone, and let's put the semi-major axis to a power. So t on the vertical axis, the semi-major axis to the 2 power. Does that work? No. How about the semi-major axis to the 3 power? No, that doesn't work. How about semi-major axis to the 4 power? No, that doesn't work. And he keeps trying like that. Again, no linear relationships. So what he then tries is both of them. So he might try putting an exponent on each of them. And lo and behold, he eventually got to the point where he took the t, the vertical axis, and put t squared on that. And then the horizontal axis, which is represented by a, he put that cubed. And lo and behold, he got a perfectly straight line. He could then say t cubed is equal to some constant times a squared. And in fact, it went right through the origin. So he didn't even have to have a y equals mx plus b. He didn't have to have the b. He just had y equals mx, where y was t squared and x was a cubed. And that was Kepler's third law. So that is how science has been done historically. And it's a really good brute force way of figuring out how things are. That's exactly what the spreadsheet allows you to do. When you encounter any two variables, you can make graphs of them, and your goal is to shoot for a linear graph, because then you know it's y equals some constant times whatever you have on the horizontal axis. So whatever you have on the vertical axis equals some constant times whatever you have on the horizontal axis, plus a constant if it doesn't go through the origin. But even that's acceptable. That's another discovery if you get that it doesn't go through the origin. All right. Any questions on that? That's somewhat, it might have been easier to explain if I'd been using say a dry erase board or even my iPad or something like that. But I think y'all can picture y equals mx and y equals mx plus b pretty well in your head. Anybody have any questions on that? I'm sorry for stopping to drink, but my throat will lose the ability to project a voice pretty soon if I don't. So, all right, looks like y'all understood that pretty well. So let's go to share screen. I'm going to walk you through how you can do something like make graphs and do regression analysis or something like that. So I'm going to share my screen, and specifically, I'm going to share it with my spreadsheet, which is right here. Okay, so now you're all Yes, go ahead.
Are we submitting this as a PDF as well, like the Excel sheet?
Yes. Well,
Okay.
actually, not this particular sheet that I'm doing. If you look on our Canvas page, you'll see that I put spreadsheet. I think it's called spreadsheet review. That's the Word
Uh-huh.
document that you'll download and put entries in and turn back into us.
Oh, okay. Thank you.
No problem. All right. So let's leave some room over here in the corner. I'm going to call this column right here. I'm going to call that time in seconds. Okay. And then I'm going to call this column right here, let's say distance in meters. Whoa, supposed to be lowercase m. There you go. Okay. Now, I would like to just generate some numbers. So let's do 0. And now here's a neat little thing you could do to make a number. When you're in a cell, and that's what these are called, each one of the little boxes called a cell. This right here is a cell in column A in row 1. So in fact, that's called A1. So that cell is A1. Well, okay. And this cell right here would be B1. And this cell right here would be A2. So on and so forth. So that's really how those work. So what I'm going to do is I'm going to make up a nice little way to do every, let's say, 1/10 of a second. So I'm going to say this cell right here is equal to, so the very first thing you type is equals. Does this need to be bigger? Well, let me make it bigger either way, just in case. So I imagine it won't hurt to be bigger. Oh, actually, I forgot. I'm still in control of that. I'll make it bigger in a second. So I'm going to say equals, and I want to take the thing above it and just increase it by 0.1. So I'll say plus 0.1. Now I'm going to increase the size. So make sure everybody can see pretty well. Okay. Now, because I've done that, I've given a formula that refers to the formula above it. Specifically, it says, take my formula, take my number from the column right or the cell right above. That cell was called C6, and add to it 0.1, and that's what I want here. Now, in general, you could just read that as, instead of taking it from C6 and adding 0.1, it's just automatically taking the thing above it and adding 0.1. So if I wanted to do this for all of them, I could use it in that generic result way by taking this box in the far right corner of the cell and left clicking on it and then pulling it down, let's say to 30. Okay. That gives me 2.4 seconds. I think that's plenty good. Let's see if I can make this a little bigger. I don't know if I want to go more than that or not. Well, let's try it again. Let's go up to 3 seconds if we can. That's 2.5, 2.6, 2.7, 2.8, 2.9, 3 seconds like that. Okay. So now we got 3 seconds. Now, we really know in physics, especially in lab, that 2.0 and 2 and 2.00 and 2.000 are all the same things mathematically. What do I mean by that? Well, if you take 2.0 and subtract from it 2, you get 0 on a calculator, right? That being said, they're not the same experimentally. For instance, if you tell someone you want a device or a thing made at a machine shop, and you want it 2.0000 meters, that's going to cost you a little bit of money. But if you want it 2.00000, in other words, 5 decimal places instead of 4, that's probably going to cost you a factor of 10 more dollars. Okay. And in a lab situation, the same is true. The more precise you get, the more difficult it is to do. And it's not just, they're trying to rip you off by charging you more. It's that it literally takes a lot more work. So it's often important in our labs to make sure we don't just randomly write a number as 2 without thinking about how many sig figs we have or how many realistically measured digits we have. So one way we can express that in there is we can click on this column, and then I do a right click, And I will go down here and say format cells. And I'll put in number. And now notice it says decimal places. Are y'all seeing the small format cells box on your side?
Yes, we're
Yeah.
seeing it.
Okay, so I was worried about that. All right, so I like 2 decimal places because that's pretty reasonable. We could do 3 if you wanted, but the main thing is by doing it that way, now it's automatically going to show you that digit. Okay, so not only did I explain something to you about the difference between 2.0 and 2.000, I also showed you another thing about using for how to use Excel. Also, I don't like, the way this variable is set up. The time t is actually just left centered instead of our left. What do they call it? It's based to the left as opposed to centered. I really prefer this as centered, so I'll do this. And there's a couple different ways. There's center vertically and there's center horizontally. I'm doing center horizontally. The same thing with this. I'll do the center horizontally. It just makes that a little neater. Now, we happen to know a formula that gives us an expression for the position as a function of time just from physics 241. So let me kill this first. And what I'm going to say is initial velocity meters per second. What I'm going to write right here is I'm going to say this quantity is, and let's see. I'm using a very specific velocity for a very specific reason. I don't really want to, calculate 19.6. But in other words, if I did a number more complicated, which was I was originally going for, a number like 7 times 9.8, you don't actually have to physically calculate it because this Excel spreadsheet is in fact a calculator. So I can just put that there just as a formula and it'll automatically give me the right number. I'm also going to say gravitational acceleration, or G, in meters per second. I'm going to say, according to our coordinate system, I'm assuming I'm dealing with a ball that's been thrown up, and I just called that velocity positive. That means up is the positive direction. So that means gravity, the gravitational acceleration, is pointing downward. So that should have to be negative 9.8. Okay. So I now have a variable. In other words, a variable representing the initial velocity. We would normally call that v sub 0 or v sub o, depending on how we write it. In spreadsheet world, we'll just call that b1. And we have an acceleration we would normally call g or negative g, but in Excel world, we're going to call b2. Okay, so I can go back and refer to that as I want. We know that the formula for position as a function of initial velocity and time is x is equal to 1/2 at squared plus v0 t plus x0. So I could also put initial position I'm going to say in meters, and I'm going to say that is, let's say that's 2.00 meters. Okay, I did not make the this column have 2 decimal places, so it's not necessarily showing that, but that's okay. I don't care. So our formula, remember, is x is equal to 1/2 at squared plus v0 t plus x0. So right here, I'm going to say x is equal to 0.5 times the acceleration, which we said the acceleration is going to be b2. So, and I may make mistakes on purpose here, so just don't try to correct me right now, because that actually could be helpful. If you find the mistake, just roll with it. And I'm using it as discovery for those of you who haven't had Excel stuff before. So times the acceleration, and then times the time, which is this quantity right here, only that has to be squared. Notice how I use the shift 6. That's what that caret key is. There's other ways your Excel allows you to use, I think it's a function called power, P-O-W-E-R, where you put in the base, you put power equals power, parenthesis, the base, comma, the exponent, and then close the parenthesis. So that's another way you can do it, but I've found that the caret symbol, the hat symbol works pretty well as well. So that's our 1/2 AT squared. The formula is 1/2 AT squared plus V0. Well, our initial velocity is this guy, B1, and that's times the time again. So I'm going to click over here, plus X0, and that happens to be B3. So that's exactly right. At t equals 0, since we said the initial height was 2 meters, we'd expect that at t equals 0, you get initial height of 0. And this is confirming that. Now, the problem is if I pull down this, it might not look right. And the reason being is when I look at this formula, notice it says 0.5 times B3. Well, B3 is not the acceleration. B3 is the initial position. So something went horribly wrong. Well, that's okay. Excel has a way to keep that from happening. Notice when we drag a column down or drag a cell down, it automatically takes any inputs that you put in there, like B1 or X22. And when you pull it down, it ups it to B2 or X23. But you can keep it from doing that by just putting a dollar symbol in the formula. So if I put a dollar symbol in front of the 2 here, whoa. So it's B2. Now I'm going to put a dollar symbol right here, just in front of the 2, because the 2 is the row. Let's see what happens. And now also, by the way, when I pull down, the B1 is going to happen as well. So I'm going to put a dollar symbol in front of that. And I'm going to put a dollar symbol in front of the 3. Now, when I pull it down, we know that after 1/10 of a second, if the thing had a constant velocity, it will have moved 1.96 meters upward. So it'd be at 3.96. But it doesn't have a constant velocity. It has a velocity that's being decreased by this acceleration. And that acceleration is basically 0.5 times 9.8, which is 4.9, times the square of the time. Well, the time that has transpired since then is 0.1. So if I'm doing this calculator on the side, so you guys can try it as well. Do 0.5 times 9.8 times 0.1 times 0.1, and you'll get 0.049. So if it was moving at a constant velocity after 1/10 of a second, you would expect the velocity to, or excuse me, the distance traveled to have been velocity equals distance divided by time. Our distance is equal to velocity times time. If I multiply 0.1 times 19.6, I get 1.96. So 1.96 added to 2 gives me 3.96. But now I have to account for that acceleration, which is 0.049. If I subtract that from that figure, I should get roughly 3.911. That's roughly what I get if I did my calculations right. So that's what we expect this next number to be if we did it correctly. So let's now highlight that box, grab the little rectangle or the little square in the bottom right corner and pull down with it. And I get exactly 3.911, exactly like I thought. Okay. Notice I just broke up the kinematic equation, x equals 1/2 AT squared plus V0t plus x0, and thought about the V0t term. That's basically what happens if there's no acceleration. The 1/2 AT squared term is what happens if there's no initial velocity. And I just treated those parts separately and predicted what this result should have been just to make sure it was right. Now that I have that, I can copy this all the way down, and this will give me the position as a function of time for all of those values. Now I'm going to change the format of these cells to number, and I'll go ahead and do 3 decimal places because it seems like that's all we're ever going to need here. I'll do like that. Okay. Now notice what I did is I put a $sign up here. Can everybody read that? I know it looks pretty small. I don't know that I have much of a way to change the size of that. But you guys can see that it's 0.5 times B $2, right? So the $sign just says, hey, lock down the variable to the right. So the variable to the right of the B was in fact the row number. And because I pulled down, I was supposed to increment the row number by 1 each box I went down. That $sign says stop that. Now you can also pull that box to the right, for instance. And if I did that, I would need to put a $sign in front of the B if I wanted to consistently get the same box. But I wouldn't need one for 2 in front of the 2. I could just say $sign B 2. And it would always pull from the second row because I'm going to the right. In principle, you can just do both of them and that will hold all of them down. So notice how we've got a graph right now. I'm just going to change this. Instead of saying B $sign 2, I'm going to say $sign B $sign 2, and you should not see any change. The C I want to increment because that's the column for the data for the time. So I'll put a $sign in front of that one too, and I'll put a $sign in front of this one, and you'll see that it doesn't change. I still get 2 meters. Let's see if I still get 3.911 and 5.724. So you see that didn't change at all. But the main thing is I'm trying to teach you that if you put the dollar symbol in front of the row number, that keeps the row from changing. If you put the dollar symbol in front of the column letter, that keeps the column from changing. If you put both, it keeps both of them from changing. Okay. So you can almost always use the $sign in front of both of them, but you don't have to. So if you want to save yourself a little time, that's nice. So now what we have here is a actual distance versus time graph of an object thrown up with some initial velocity and pulled down with some acceleration. And it appears to be getting higher and higher and higher until, notice it goes 15, 16, 17, 18, 19, 19, 20. Actually, it continues to get higher. Let's check my math. Okay, yes, it starts to crest over down here. Yeah, go ahead. Question? No one has a question? Okay, what I was looking for, I forgot I did increments of tenths in a second. So go ahead.
I know there was questions in the chat room. I don't know if you saw them though.
Oh no, I had the chat up and it disappeared. Okay, yeah, let me check this. What happens if you put a $sign B2? Yeah.
You already answered that question.
Gotcha. Appreciate that. Yeah, but if I did that one, notice that would just keep the column from changing, not the 2. So the 2 would keep on moving. That would screw up. But thanks for asking that, John. Sorry, I didn't see it. I've got the chat window open now. Just forget to do it and I switched to panes. All right, so we now have this. I think you all understanding. Remember, we set this initial velocity to 2 times 9.8. That means if you remember our equation, V equals V0 plus AT, that means it's going to take 2 seconds for it to reach 0 velocity in the vertical direction. So at 2.00, that should be the max height. And lo and behold, look at it. It is. It got all the way up to 21.6. Before that was 21.551. And before that was 21.404. So symmetrically, on the opposite side of 2 seconds, when you go to plus 0.1, you're going to get the exact same numbers, 2.51, 21.551, 21.404. So you can see this is actually where the peak occurred. That's where the actual peak occurred. Oops, typed in the wrong area. So that's where the peak occurred. And that means the graph is going to look something like this as a position as a function of time graph. Now, we should do that. We should see what that graph looks like, and that's going to teach us something else, i.e. how to graph things. So I've got these 2 columns, and I can just highlight them like this. And then I can go insert. Notice I've got a header up here that says insert. And then we can wait for my Macintosh processor to take forever. And over here, I can see there's graphs. And in fact, the one that we want in science is a scatter plot. We never want to connect the dots in a science graph, okay? Never, never, never connect the dots. We do what we call curve fitting or trend lines, that sort of thing. We do not connect the dots. So I'm going to click on here and it gives me various options because it's got a little arrow there, but I want the dots without the lines connecting them. So I'm going to choose this one. So does everybody see what I pushed? I selected the two columns, the what I'm going to plot as the independent variable, specifically time, on the left, and what I'm going to plot as the dependent variable, distance, on the right. I copied just the numbers without the headings. You can actually calculate, include the headings, the time and the distance, for instance, where it says meters, and it'll know good enough not to mess with those. But anyways, now I click insert, and then I went to scatter plot and chose this particular plot, and it should automatically just make a graph. And let's see, what you got to check is that they didn't just take the distance, because sometimes if you don't, if you don't do it correctly, sometimes Excel will make a graph of this column, but just versus the line numbers, and it'll look almost the same because line numbers increase sequentially, just like the time did. So I always take an extra second to just click on a data point or hover over a data point and find out whether that's actually a data point or not. So I've got a time of 0.30 and a distance of 7.439. And that's exactly one of the data points I see. So this is graphed exactly what I wanted to graph. Okay. Now you can do more stuff with that. You can double click on this and make a title. You can, for instance, call this height in meters versus time in seconds. That's a nice title if you want. You can also do things like click here. I clicked on one of the Y values, and now I'm right clicking it, and I can do format axis. And you'll see a window pops up here. I can choose to do the maximum and minimum. Oftentimes the graph won't start until like, Y equals 100. This would be a good time for you to type in the minimum to be 100, and maybe it only goes from 100 to 125. So then you'd put the maximum at 125. You can also make the units at which lines are occurring. In this case, every 5 gets a line. That's why it goes 0, 5, 10, 15, 20. If I wanted to, I could do 1.0 and it would get really crowded. But you can see, yeah, that's clearly a lot of numbers. You can display the units if you wanted to. You can use a logarithmic scale. That would actually graph the log of this if you wanted, and so on and so forth. But you can also do things like you can add, change the tick marks. That's the little marks that are on the side of here. You can label it. So the label position is next to the axis. And you can alter the numbers to show whichever way you want. Obviously, we don't need that many decimal places. So we could actually change it to a different format or stuff like that. But anyways, this is some of the stuff you can do with the data. You can also do the same thing here. And I clicked on one of the numbers, and again, I do format axis, and you see you got the same sort of things, same choices we had before. As far as text options go, you can do a text fill. I didn't show you this on the other one. Or you can do a text outline. Again, it doesn't mean very much here. What I'm showing you is these features are here. Type in them and see what happens all you want. I want you to experiment with it. You can't break anything. Experiment with it and find out how to make this graph look the best. Like, it might be really nice to take that vertical axis and put a variable next to it to represent time, or excuse me, to represent distance. So you might write X or D or something like that. But you might also want to write it up and down instead of horizontally. There's ways you can do that by playing with these various features. Now, of course, that setting that I had mark every individual second was a little brutal, or every individual meter was a little brutal. So I'm going to go back to format axis and change it back to 5, just because that was ugly. Well, I can do it right there, 5. That basically says do what it was before. So I did that. So now I got something fairly neat. That's nice. What I also can do though is I did format axis. What happens when I hit format major grid lines? Now the grid lines is saying they're automatic. Their color is white. I could change them, for instance, to or excuse me, their color is gray, I guess. I could change it to blue and I get pretty lines like that. Ain't that beautiful? So beautiful. Okay, I go like that. It'd be too thin, too dim. I do it like that. It'd be pretty good. You can see it's still not the same thing I had before. Let's try this one. Now that's what I had before. So you can do that. You can make the style to be dotted or dashed or something like that. There's all sorts of stuff you can do with that. You can also, let's see what else options come up when I click this. Font, you can change the font. You could change the graph type. We don't want to do that. Add, no, do this. No, all that's good. If you wanted to, you could actually add, there's a couple of different ways, but you can choose from a graph like these up here. Those are different chart designs you can use. And some of them will have automatically built in a variable here and a variable here. If you use one of those, then you can automatically title each axis as well, but it's not really required to do. But I do want you to try to figure that kind of stuff out. But now let's ignore for a second that we have this data that we generated by formula. Okay. And what I'm going to do now is try to find a curve fit that fits this really well. So in everyday life, you would make a graph. And remember, I told you about making a straight line graph, how Kepler did that. Well, a straight line graph is one of the few that we're really pretty good at as humans, making an estimate of what a true curve fit is. So for instance, if you had a plot of y equals mx plus b, there'd be a bunch of lines making sort of or a bunch of dots making sort of a line. Let me stop sharing this for a second just to talk to you. So what I'm going to do is actually try to pull it up on a document cam. I mean, on my iPad. Oh, great. I turned my iPad off, so that's not helpful at all. I guess there's probably another way of doing it, but we'll wait for that. So I told you the importance of y equals mx plus b, or just y equals mx if it goes through the origin. The reason being that we want to reduce it to linear is one thing, that is the best way to do a human curve fit. So a human curve fit basically takes a graph of y versus x, and it'll have all these dots, and they usually should form somewhat of a straight line. If they don't, you'll see at least somewhere at the far end of the data or at the near end of the data or just in the middle of the data, some of those parts will deviate quite a bit from the actual predictions of the equation that you're using. And when that's the case, you have a sense that it's not really linear. So that's the stuff you got to look for. But the reason doing linear is so great is all I have to do is lay, say, a clear ruler across all the data points until the edge of that clear ruler is in some sense minimizing the total distance between, and I mean perpendicular distance. So for instance, you're taking the edge of the meter stick or the edge of the clear centimeter ruler, you're taking that edge to be a line, and you imagine a bunch of little lines perpendicular to that shooting out from that edge, touching the individual dots. And then each of those individual lines pointing from the edge to the dot, you measure that distance, measure that distance, measure that distance, sum them all up and see what the number is, and then adjust the meter stick or the ruler just a little bit to see if that sum's smaller, or a little bit more to see if it's smaller. And you try to minimize that. In other words, you try to make the least deviation of the graph. So what I'm going to do now is my iPad's finally on. I'm going to make a new document. Take me just a second, everybody. Hold on. So PHY242 L01B. This is 01. Today's the 18th, right? 182023. Yeah, that looks good.
And now what I'm going to do is attempt to share screen again, but this time with my iPad. Okay. All right, so you're now looking at my iPad, and let's imagine making a graph. So first off, I'm going to make a graph. And when you make a graph in science, what you want to do is make the graph so large that basically the data takes up the whole graph. In other words, you want the smallest part of data at, say, the bottom left corner of the screen, and the largest data point, the last data point at the top right. That way, you're sort of maximizing your ability to see the details of it. So this graph right here is going to be a graph of, let's say, D in meters, and this graph is going to be T time in seconds. That's what we're doing right now. The graph that we have in our Excel is essentially that. Now, if I had data points and they look like, I'm going to cheat a little bit here. I'm going to draw a line and then make data points close to it just because, I can. It's a pain otherwise. So that's a pretty straight line, right? So now what I'm going to do is I'm going to put a dot right here, another dot here, another dot here, another dot here. Whoa. Now this is a rather bad looking graph, but believe it or not, that's a super wonderful graph for most sciences, especially the biological sciences. When they do stuff in the biological sciences, their data does not often look linear when they call it linear. So this is really a special case of some pretty nice looking data. Okay. Now what you're doing is, I'm going to move this line over here and use it later. What I'm going to do for a curve fit is I'm going to try to create a line that seems to ideally mimic, actually, let's do this again, that seems to ideally mimic this data. Okay. Now, how I do that mathematically, what you're shooting for, so you have a concept of it in your head, even though you're not ever going to physically take the time to do this calculation. You can, you don't want to, but you can. What you're going to do is say, okay, I'm going to draw a line perpendicular to my guess line, which is the red, to that data point. And then I'm going to draw another one here, another one here. I'm trying to draw these perpendicular to the line. They might not come out perpendicular, plus it's making me do a lot of weird stuff. Oh, I see. It was on that. Okay, so now I'm going to try again to draw these little lines. So there's one, there's one, there's one, there's one, there's one. There's almost no line there, almost no line there. So these are supposed to be straight lines, but when I put them, make it automatically straighten it, it sometimes takes the little lines and makes them curves. So I'm trying to do it by hand like this. Okay, so mathematically what you'd want to do is find out exactly what those individual distances are. So in other words, the length of each of those blue lines, and of course the blue lines are supposed to be perpendicular to the red line, so I'll put that there to remind you. And you take the sum of all those for this red line and you write down a number. Okay, then you say, okay, well, that number is that, but what if I did this line? Notice how I moved it a little bit that way. And you do the process again and you move it this way, and do the process again and you move it this way, and you do the process again and you move it this way, and you do the process again. All of those are fair ideas at what a least square or what a curve fit is. Now, mathematically, they found the very best way is do something called a least squares fit. So they take those distances
and they square them, and then they add them up, and then they basically compute the minima of sort of a function, if you will. So they actually do a little bit of calculus. And by doing that, they can determine, if there's enough data points, they can determine what the slope is and the intercept is. So after a least squares regression, you get y is equal to mx plus b. That's the equation for a straight line. In our case, it would be d is equal to m t. And in this case, our curve looks like the b is zeros, but I'll put b there anyways. So the least squares regression gives you this value and this value for the absolute best curve fit. Before we had, computer or calculators that could do this, we either had to use a spreadsheet or we'd actually have to write computer programs to do this. And we often didn't just have access to it. So for instance, a lot of my experimental physics work, the little bit that I did was, because I'm a theorist, was basically making graphs by hand. So I would say, okay, what's my largest range of y values? In other words, what's the largest minus the smallest? And then what's my largest range of the x values? Okay, largest minus smallest again. And whichever one of those was the longest, I would put that axis parallel to the long axis of the paper. And I would try to make the high number end on 1 or 2 lines from the very top and the small number 1 or 2 lines from the very bottom. And then I do the same thing with the short axis. And make the very largest number, say 1 or 2 spaces from the right-hand edge, and the smallest number 1 or 2 spaces from the left-hand edge. That way I was ensured the graph would be absolutely the largest. It might prevent me from seeing what the origin is, because if the number starts way higher than 0, then obviously I'm not going to see the origin. But then I draw a line that looks like it fits the best. And I sort of think of this process in these lines, and you'd be surprised, as humans, we actually do pretty well. I would not suspect that red line to have a slope and intercept much different than I would get from a linear regression. Okay. The good news is linear regression is really, really powerful and not that hard to compute. But there's also regressions that are nonlinear, and that's when you try to make a line fit, let's say a curve path. So for instance, if you had another graph, let's draw another graph here. If you had a bunch of data points that look like this, all those little data points, that does not look like a straight line. So you might want a line of best fit that maybe looks like this. Okay, that looks pretty good. That's a second order polynomial, at least assuming it doesn't make any more turns around. If it makes any more turns around, that's going to be a third order or fourth order or something like that. But you can do a least squares fit on that one as well, only it's not a linear regression, it's a nonlinear regression. But the good news is Excel does all of those. Okay. But when you talk about what Kepler did, well, he didn't have access to that regression. We hadn't invented the mathematics behind calculating that regression as well. So he just had to graph things on a linear axis and then do his best guess of what the curve fit was. So this one's a non-linear one. He couldn't have done that, but we can. Whoa. So everything we do in science still uses that idea. We want linear graphs, specifically because the linear regression actually has less error, requires fewer data points, and all that good stuff. Whereas you do a second order polynomial, third order polynomial, all of those are really good and can get really accurate results, but it's not necessarily as easy and as precise as a linear regression. The other ones, you need a lot more data points. So you could probably do a linear curve fit with 5 data points. The minimum, of course, would be 2, but you could do it with, like 5 data points, and then linear regression would give you pretty good results. But if you tried to do a curve fit like y equals some constant times x squared with 5 data points, you get a buttload of error. You'd have to do it probably more like with 25 or 30 data points. So the linear regression is still sort of the holy grail in the sense that it's the one you can do with the least amount of data. Okay, so let me stop sharing screen again. So you've now seen how that goes. Let's do that with our Excel spreadsheet now. So I'm going to share screen this time with Excel. And yes, we generated this formula, but let's see if Excel is really smart enough. So what I would like to do now is I'm going to take this graph. I just clicked on that. I clicked on one of the dots, and now I'm doing a right mouse click, and you see add trend line. So this is a step that you're going to take, and different, if you're using the non-Mac version, they might have a slightly different way of doing it, but you got to find add trend line. If you can't, just go up there where the little light bulb is. It says, tell me, just do a search for the word trend line, and it'll show you where it is in Word. But I'm going to do add trend line. And you'll notice it's got all these different options here. It's got exponential, it's got linear, it's got logarithmic, polynomial. If it doesn't, sometimes they'll just automatically spit up a linear. That means you need to go a little deeper because there's a whole other set of options behind it. So what I'm going to do is I'm going to say this is a polynomial. We know the actual equation is d equals 1/2 a t squared plus v0 t plus x0. And we know that's a second order polynomial, but and it's given us an idea. Hey, we think this is a second order. As soon as I clicked in polynomial, it said, hey, I think this is a second order polynomial because it's smart enough. But let's just, for the heck of it, let's force Excel to the max and force it to be a third order polynomial and see how it handles that. Okay. Now you can do things like set the intercept. That means you can force it to go through the origin if you wanted to, or something. In this case, I would probably want to set it to go through 2 meters, but I'm not going to do that now. But the main thing you want is you want it to display the equation that it found from the linear regression, and you want it to tell us how precise that was, because this r squared, the closer it is to 1, the closer the curve fit is to being highly precise, or very good, in other words. So you want both of those clicked, and now you've got it. Check this out. It says the equation, look at this number, -2 times 10 to the -13th. That's literally a 0 followed by 12, followed by a decimal point and 12 zeros, and then a 2. So essentially this cubic term is essentially 0. So it was smart enough to actually figure out, yeah, he wants to force this to be a third order polynomial, but it's clearly not. I'm going to have to push that exponent or that coefficient of x cubed down until it's essentially 0 to make it make any sense. And that's what that front term did. But notice what the second term, the square term, does. It's -4.9. Well, that's exactly what we programmed in. It was 1/2 of 9.8, and half of 9.8 is 4.9. And not only that, we used -9.8, so it comes up to -4.9. Remember, the next term was plus the initial velocity times time. Well, the initial velocity was 19.6, and we see that, in fact, they got exactly 19.6, and the initial position was 2.00 meters, and lo and behold, it got 2.00 meters. And notice it's got r squared equal to 1. 1 is the perfect. Now be advised, you can sometimes find r is equal to 0.99999, 5 nines in a row. And then you can find another graph and it'll be 0.99999 again, only you know what it's supposed to be versus what it's not supposed to be. And the least squares fit is actually giving you 2 values or 2 equations with equal values of r squared, and you need to decide which one's the best. So that sometimes does come up. Don't just assume the r squared being close to 1 is enough for it to be precise. You can actually get a lot of different r squared values by changing the function. You could, for instance, change this as a part of a sine function because it literally looks like part of a sine function, and you get a really good R value, but it's completely wrong, right? So keep that in mind. This whole thing here, this whole document is basically a recreation of a curve fitting process. So I'm taking the data that I graph, which it pulled from those two columns, and I'm doing a nonlinear regression. I'm doing a second order polynomial regression. Actually, I did a third order polynomial regression on it and got exactly the right equation that I wanted. And that's what you're trying to do with this lab is you're learning how Excel works. You're going to let it make linear regressions and so on and so forth. So anyone have any questions on that? I'm going to go ahead and save this. Okay, so it looks like y'all understand the process. Probably you're all familiar with it anyways. I've been talking for an hour now. That's plenty of introduction. So what I want you guys to do now, let's see if I have this ability. Let's go. I'm going to go back to my modules on my page. One thing, hopefully you guys noticed, I put some more links to videos up in week 1 as well as in week 2. One of which answers a question that some students in my class had. So let me share my screen again now, but this time I'm going to do it with Canvas. Okay, so then now you're looking at my Canvas course. And you can see, remember we have week 0, which has stuff that you might not be that familiar with if you weren't in my class before. Like you need to know how to add and subtract vectors by drawing. You need to understand the basics of sig fig, scientific notation, unit and dimension. This, in case you're rusty on adding vectors, this is a really good intro to that. Cartesian coordinates, which my class ran into last night, you'll run into today, the different coordinate systems, because we're going to start Gauss's law today. Those are all there. But what I added since last week, was this Canvas will not open a YouTube link. Because when you click on these, what's going to happen is this goes to my YouTube. Notice it says refuse to connect. That's okay. It's a thing built into Canvas, but all you have to do to remedy that, and the video shows us, is look up here. You'll see the title, and I just click there. It probably works if you click there, but for some reason I've always been clicking there. But if you click one of these areas, it should open up a brand new tab in your browser and open up the document. So let's try just clicking on this, since I always do the box. Oh, that was a pretty face, wasn't it? All right, shocked you, just jumps right out at you. So anyways, it does work. You can actually access these pages. It's just a matter of a 2-step process instead of 1. So do notice that week 1 has that week 0 is there, which I'd already told you about, but do notice that week 1 has been I've had a few videos added. That one was just to deal with that technical issue. This is a version of the calculation, that really brutal integral I calculated. This is another instance of me doing that. And it's something that you can use to review, because I made an extra credit problem down here that you probably should all do just to make sure you can do this type of problem. And that requires you to be able to do this one. Only the difference is I'm not going to integrate from negative infinity to positive infinity. I'm going to integrate from negative L/2 to positive L/2, and or you are in the extra credit, and you're going to get an answer. And then I'm going to get you to see for a given distance, say 10 centimeters away from the quote unquote infinite rod, how large does the rod have to be for the difference between that and the infinite formula to be off by 0.1%. So only by 0.1%. So that's the problem you can do. There's calculation Coulomb's force, not unlike the ones we did in class, but also including vectors. Here's another one for Coulomb's law. Here's another one for Coulomb's law. And here's another integration for Coulomb's law. So these are all examples from my YouTube channel. I highly recommend you watch them. Obviously, you got the examples in your book, but that's there as well. So you've got that. Here's your spreadsheet review. That's the lab we're working on today. And I'm now getting ready to take this document that I just made. I have these blank windows, these blank modules like this, leaving them open, because when they're open like that, I can just drag and drop. It won't let you drag and drop into like this module. I couldn't drag and drop that from my hard drive to here. So I'll put that there, but there's your spreadsheet lab intro, the actual lab the actual Excel sheet that I just wrote out, that's right there. And I'm going to put a turn in place right there for that assignment. No. So notice also that week 2 has the invitation for the Zoom. That was the one we just did for lab. This is the one we're going to do for lecture at we meet at 2. So at 2 o'clock, you'll use this one. Here is an introduction to Gauss's law and flux, which is what we're going to cover in class today. And here's electric flux doing a surface integral, because that's part of the quote unquote vector calculus that we're doing in this class. But it is actually, it's a lot easier than it seems. So there's your homeworks. Any questions on anything now? All right, I'm going to stop sharing while you guys go to your breakout rooms, and you're free to, you don't have to stay in the breakout room to work. I think this is a lab that works perfectly well. You doing it by yourself, but you really need to communicate with each other if you have the least bit of misunderstanding or confusion. So what I'll do is I'll open up the lab rooms. We've got, let's see how many people we got in the class. We got 16 of you guys in here. So I will open up 4 breakout rooms. What I suggest you do, if anybody definitely wants to stay, maybe you chat that out to everyone, and then the people that want to stay can all go to the same room number. Let's say all the people that say they definitely want to stay, let's have you guys go to breakout room 1. So let me do my breakout rooms. I'm going to create 4 breakout rooms, and I'm going to let the participants choose. Now the 4 rooms are open. So what I would like you to do, anybody that wants to definitely spend at least the next, let's say, hour, up to an hour or say, on doing this, I want you. Oh, thank you. I appreciate it. It's a whole B to broadcast to all the rooms. What I want you to do is, if you're definitely wanting to be here and work on this in real time right now while I'm still here, chat that, post that in the chat, and then everybody should be able to see that chat. And anybody else that says it, all of you go to room 1. If there's more than 4 of you, let it go to room 1 and 2. If there's only like 5 though, then do 2 in room 1 and 3 in room 2, or 3 in room 1 and 2 in room 2. If it's 6, do 3 in each, that sort of thing. Okay, so everybody go ahead and chat your desires, and then anybody else wants to go, they can go to the other rooms. I'm going to stay here until the last of you guys leave, and I'll be fixing on our grade book, but I'll be right here out. You just have to come out and either call me from in there or come out here and talk to me. So everybody's free to go now.
I had a question.
Yes.
For the lab, on like page 2, I guess, for graphing basics, do we
Right.
just graph the data that we produced on the first page?
Yeah, that's what they're wanting you to do. And you don't have to like do any printing. You can just take a screenshot and insert that in the Word document wherever they ask for it.
Okay, thank you.
No problem. Feel free to give more than they ask for. Like, I like to see the data columns, even if they didn't ask for them. I like to see a separate graph, even though they didn't ask for it, so on and so forth.
Okay, thank
Looks
you.
like I got 3 people on room 1 that are definitely planning. I suspected John Wells would definitely be one that was going to stay. He's in room 4 with his friends that he knows. And it looks like about everybody except for Jessica and Ryan, or excuse me, Alex. Do you have any questions, Jessica or Alex?
I'm gonna work with Grace Hopkins on the
Okay.
lab. We're just gonna FaceTime.
Okay, that's cool. No problem.
Thank you, sir.
I will stick you in that room. Just oh, Grace Hopkins, they didn't go to a room either. So let me see. You're still counted for being here. I'll just put you in room 2, and I'll do the same. Ryan, in case he's here, I'm going to put him in room 2 as well.
Okay, thank you.
No problem.
Grace.
Oh, Alex went somewhere, I think. Yep, Alex ran away.
Just in case, Jessica, I'm gonna not put you in room 1. I'm gonna put you in room 3 where there's people in case you want help. Okay,
Thank you.
no problem.